Hi guys, and this is Friday, and today I'll be showing you my version of CS50's Intro to AI Project 5, the traffic program. So as research continues in the development of self-driving cars, one of the key challenges is simply computer vision, allowing these cars to develop an understanding of the environment that they're in, forming from digital images. In particular, this involves the ability to recognize and distinguish between different road signs. For example, stop signs, speed limit signs, yield signs, and many more. In my project today, I'll be using TensorFlow to build a neural network to classify road signs based on an image of those signs. And to do so, I have a labeled dataset with a collection of images that have already been categorized by the road signs represented in them. So there are many different datasets that exist, much for the same purpose, but for this project I'll be using the German Traffic Sign Recognition Benchmark, otherwise known as the GTSRB dataset. It contains thousands of images of 43 different kinds of road signs, and according to that, my program, or AI, will be able to classify each of those road signs. So for the program, I've employed a number of techniques. Number one, I'll be using a set number of convolutional and pooling layers, different numbers and sizes of filters for my convolutional layers, different pool sizes for pooling layers, different numbers and sizes of hidden layers, and different sizes of dropouts, all ultimately to build a perfect neural network. But of course, I'm going to make it as accurate as possible. So let me run this program. Let's go. Python 3 traffic.py GTSRB. Let's run this. Okay, so here we can see all the files and data and images are being loaded. From there, we can see that I'm going to be training on 15,984 samples. Okay, so let's wait for all of these samples to be going through. So it seems like we have 10 different times we're going to be doing this, and over here, of course, Python program will be able to show us the estimated time, the amount of loss that's occurring, and ultimately the accuracy of my program. So this cycle will run 10 times, hopefully increasing the accuracy each and every single time. So let's wait and see what will happen. Okay, so now we're on f(2) out of 10. Once again, it's going to be testing the model. So just out of interest, if you want to know how many convolutional layers etc. that I've used, I'll state it now. So for convolutional layers, I've used 40 filters with a 3x3 kernel. For my max pooling layer, I've also used a 3x3 pool size. For my dropouts, in the flattening section, I've used about 0.2 dropouts. Of course, to prevent overfitting, because an over-reliant model may not be as accurate. For my hidden layers, I've used 3 different hidden layers, hidden layer 1, hidden layer 2, and hidden layer 3. My first one has 40 different individual sections with a dropout of 0.3. But then for 2 and 3 individually, 2 has 20 different units, while 3 has 10 units. Ultimately, if we use more layers and bigger sizes, then it can make our model much more accurate and can be used to provide more complex features in the program. But ultimately, this is quite a simple program which only determines 43 different road signs, so we may not need as many layers and hidden layers, etc., as it's not as big of a complex neural network. But of course, as we build up on sizes, we may need to have more and more links in the neural network. As that happens, the neural network size can heavily increase. And in each of these processes too, we get the image, then we go through the convolution stage, providing feature maps, and then we learn what filters there should be. Then we go to the pooling section, where it's made into smaller pixels and grids, and it's been done. It can be done in n number of times you want. Because if you make it smaller, it might be able to see more in-depth features and more specific features. For example, first level features in compared to second level features, low level features, and high level features. So with low level features, you can see stuff like edges, curves, and shapes. While in second level features, higher level features, we can see much more clearer objects. But that depends on the program. Okay, let's just wait and see what happens. So we're halfway through it right now. And as we see here, you can see that the accuracy has been increasing very much, especially the big jump between Epoch 1 and Epoch 2, especially since there's much less loss. And it's also much more accurate, a jump of about 0.3 in accuracy. Hopefully you can hit 90% this time around with accuracy. It seems promising. We're getting 0.92 accuracy, a bit higher than Epoch 5. Seven out of 10, about 91.72% accuracy, a significantly lower loss though. Accuracy is building up. It seems like it's reached 91.78. Hopefully it goes a bit higher. It seems like the accuracy kind of dipped. Hopefully we can get it more accurate on Epoch 9. Of course, the more accurate a neural network is in the model, then the better it will function. And also, let me introduce a basic foundation as well. I'm using TensorFlow, which is actually a machine learning library that can be employed in Python. It's simply a library that you can use for creating a neural network, and it gives you more decision boundaries which are more accurate and can build a more accurate model of your neural network, making it more complex and allowing things like I introduced at the start of the video, the stuff about computer vision. If you don't know what computer vision means, it simply means computational methods for analyzing and understanding digital images around us. Basically for image convolution itself. It's for applying a filter that adds each pixel value of an image to its neighbor, and according to that it can create weighted values according to the kernel matrix. And through this process it's been able to calculate an accuracy level and also build up this image. My dataset's actually been split up into both test set and a normal dataset. So that's where all of this testing occurs with the accuracy. Okay, our final accuracy seems to be 90%, which is pretty promising actually. actually. Maybe if we reduced the dropout function, maybe it would have been a bit more accurate, because it would have resulted in less overfitting. And also, we see our loss is 0.3934, which is not too bad. So, let me go and show you one more thing. So in terms of the images that we have a couple of images that we can use. But that's pretty much it. Just images such as this one, or this one. All of these are traffic signs, and there's several different versions of them that we use. And according to that, it builds up an image. But anyway, that's it for the video. Thank you very much for watching. I'll see you next time.